Hello friends, good afternoon and welcome to EduSet live lectures. Dear friends, as you know that we have started a series on organic chemistry and today we are conducting yet another lecture in the same series. In today's lecture we will be continuing with the reaction intermediates and it will be the second lecture in the series. To discuss this topic, we have with us our subject expert Dr. Pankaj Khanna. Dr. Khanna is Assistant Professor in Department of Chemistry in Acharya Narendra Dev College, University of Delhi. Without further ado, I would like to welcome sir to our studios and request him to start the lecture. Welcome sir.
Thank you so much. Hello viewers, we last discussed about the reaction intermediates, what are the types of reaction intermediates in the carbon chemistry, and then we talked about in detail about the carbocations, one of the intermediates well known for organic compounds because of the positively charged carbon atom which is prevalent. Now in today's lecture we would be talking further about the intermediates, other carbon intermediates which are the carbanion and the free radicals and the carbenes. So let us start with the carbanion intermediate. We did the positively charged carbocation intermediate which is called as carbocation. So in place of that, if the group which moves out is leaving the shared pair of electron, then we get this type of an intermediate. We have already talked about this in the previous lectures, and we get a negatively charged ion. When it is a negatively charged ion of carbon, it is called as carbanion. So this carbanion, as you can see in the structure, is like for the structure in case of carbocation is sp2 hybridized because one p orbital was pure orbital, but in this case the tetrahedral sp3 geometry of carbon remains as such, and the one of the sp3 orbitals gets the lone pair of electron, that is a negative charge, and hence we will see that there are 3 bonds going across like this, and they would be in a 120-degree angle, and with a lone pair taking up this place in a tetrahedral geometry. So the final geometry which comes out to be is it is sp3 hybridized, but according to the VSEPR theory and the lone pair bond pair repulsions, it turns out to be from sp3 tetrahedral to trigonal pyramidal. So it takes a shape of a pyramid, and carbon being the center point of the top point of the pyramid, and lone pair is above it. So this form is of the carbanion. So last time we did about carbocations, in the same manner we can say that the stability order of carbanions also, as we discussed about the primary carbocation, the carbon attached to one carbon atom is primary, with no carbon atoms all the 3 hydrogens is methyl. Same is the case in the case of carbanions, methyl carbanion, then primary carbanion with one carbon, one methyl group, 2 methyl group secondary, and tertiary butyl carbanion with 3 methyl groups attached to the carbon with negative charge. So this primary, secondary, tertiary, I have already given the stability order. The methyl ion is the most stable, then the ethyl ion, then the isopropyl anion, and then the tertiary butyl anion. Why is this so? In this case there is no stabilization or destabilization according to hyperconjugative effect, or there is no possibility of resonance effect. Only effect which is possible is plus I effect of methyl group present in the primary, secondary and tertiary. As the number of methyl group increases, the electron density by the plus I effect of methyl group on carbon with a negative charge increases. Thus, it destabilizes the species as there is an increase in negative charge. A charge, whichever is the case, positive or negative, when increase destabilizes the molecule or the species. So, tertiary butyl carbanion is the least stable because it has 3 methyl groups, and there is a maximum inductive effect on the negatively charged carbon, and hence it is the least stable. As the number of methyl group decreases, the stability of the carbanion increases, and with methyl anion there is no methyl group, it is the most stabilized because there is no plus I effect. However, if we replace any hydrogen in the case of methyl anion, if we replace any hydrogen with more electronegative atoms or groups, say CH2Cl minus, chloromethyl carbanion, or any other electron withdrawing group, or a group which is less, which is more electronegative than hydrogen, there will be a pulling of the minus charge from the carbon, and those molecules or species would be more stabilized than the methyl carbanion because of the minus I effect of those atoms or groups. So, this is about the stability of alkyl carbanion. The other issues which come into picture is, we will come to the stability by resonance in a minute, but here in this case of carbanion there are other possibilities also. For that we take up the acetylide carbanion, which is generated from acetylene by the loss of proton, and this is a bit of more acidic nature because this is very stable form. This is stable than the vinylic carbanion, which is equivalent in stability with the phenyl carbanion, and these all are more stable than the methyl carbanion. Why is this so? This is because of the fact that when we move from sp3 towards sp, the percentage S character increases. So, in case of sp, the acetylene or acetylide carbanion, the percentage S character is 50%. In the case of sp2 hybridized, it is 33%, and in case of sp3 hybridized, it is 25%. So, why I am telling you about percentage S character? Because as I have already told you that if a more electronegative atom is attached to the carbon carrying negative charge, the stabilization of the negative charge would take place. So, by virtue of minus I effect, same is the case here, because in the orbitals the percentage S character determines the electronegativity of the orbitals. So, sp hybridized orbitals are much more electronegative than the sp2 hybridized, and which are in turn more electronegative than the sp3 hybridized, because a percentage S character means that they are having more S character and they are nearer to the nucleus. When they are nearer to the nucleus, then the electrons are bound much more towards they are attracted towards the nucleus much more, or they are tightly held by the nucleus. In this case, there is a pulling of those electrons towards the nucleus, and this creates an environment which says that it is just like a more electronegative atom present in the vicinity of the negative charge. So, if a more electronegative or a more percentage S character orbital is present, the more stabilization of negative charge happens because of the minus I kind of effect, which is the stabilization or dispersal of the negative charge. Hence, the triple bonded carbanion is more stable than the double bonded ethylene or phenyl carbanion, which are still more stable than the alkyl carbanions. Moving on to some other effect, like this is not the resonance effect exactly, but we are taking the help of resonance here, by virtue of which we are making this amide C double bond O N into an imide kind of a system, such that there is a positive charge on nitrogen. Again here, this nitrogen with a positive charge in this part of resonating structure, this nitrogen with a positive charge is creating more amount of pulling of electrons by virtue of the field effect or the minus I effect, and hence this minus charge is again decreased. So, these kind of systems are also very much stabilized, although we say that two adjacent positive and negative charges are not stabilized by resonance, but this is not resonance. This is by virtue of resonance we have created a positive charge on nitrogen, which in turn is stabilizing this negative charge anion which was already present here. So, these type of systems are called as violates, and these are not only present in nitrogen, but also in phosphorus and sulfur also, and you would remember that these kind of structures would be appearing in the Wittig reaction type of systems. So, these unusual systems are stabilized by virtue of the positive charge on phosphorus, which it can stabilize the carbanion negative charge. So, this is all about the special kind of molecules which are called as violates. Then again going back to the similar kind of things as we have done in carbocations, the stability by resonance. allylic carbanion, which is again stabilized by resonance by virtue of the movement of the lone pair into the pi cloud conjugation and this negative charge appearing on the other carbon. So, this is the allylic carbanion. Similarly, the benzylic carbanion also is stabilized by virtue of resonance and the electron density is dispersed in the benzene ring, giving us these canonical forms. These benzyl carbanions are again stabilized in the similar fashion as the benzyl carbocation. Again, as we discussed in the benzyl carbocation and diphenyl methyl and triphenyl methyl. So, the similar kind of stability appears in this case also by virtue of more number of resonating structures because of the presence of 1 phenyl ring, 2 phenyl rings and 3 phenyl rings. There should not be one hydrogen appearing here, it should be pH3C minus. So, this hydrogen you can delete from here. So, pH3C minus triphenyl methyl carbanion is most stable because there are more number of resonating structures because of 3 phenyl rings present, and in a similar fashion the aromatic behavior which appears because of the presence of carbanion, this carbanion negative charge denotes a pair of electrons, and when this pair of electron is present in conjugation in a cyclic system like cyclopentadienyl carbanion, then we get a 2 electron system from this negative charge and 4 electron pi system from this pi cloud, and we end up with a 6 electron system which accounts for 4n plus 2 n equal to 1 Huckel rule system, and this cyclopentadienyl carbanion is hence aromatic. Similarly, the unusual anti-aromatic which are not stable, one is like there is no aromaticity, then there is more stabilization by virtue of aromaticity which we call as 4n plus 2, and there are less ones which are unstable because of the presence of anti-aromaticity, and these are the cases when carbanion in presence of 6 more electrons makes a 4n system of, in case of cycloheptadienyl carbanion, this is an 8 electron system which makes it anti-aromatic. Similarly, a 4n system with 2 electrons of cyclopropene and the negative charge amounting to 2 electrons giving 4 electron system n equal to 1 cyclopropenyl anion is also anti-aromatic. So, these are unstable than the ones which are which do not have aromaticity, molecules which do not have aromaticity. So, these were the stability factors of carbanion. Now, let us move on to the reactions and what are how the carbanions are generated and how they are reacting with the further in the further reactions. So, what is happening in the generation? Carbanions are generated by virtue of the acidic behavior of a carbon hydrogen bond. So, basic approach or basic reaction which happens is the one where if a carbon hydrogen bond turns into a carbanion, then the carbon is said to be acidic, as in case of acetylide ion C triple bond C minus, which is getting from acetylene or ethylene. What is happening that CH bond is getting broken and it is giving a C minus. So, other than that, the generation of carbanion is by the reaction of a base with some of the species which are acidic in nature by virtue of resonance. We are coming to that, and the best example for that is aldol condensation. So, you can see the slide in what happens in aldol condensation. This alpha aldol condensation happens only with the carbonyl compounds. It does not happen in formaldehyde where both the groups are hydrogen and hydrogen, or in case of benzaldehyde where both the groups are pH and pH phenyl rings, but in the case where alpha hydrogen is present. So, alpha hydrogen is present, this is an alpha hydrogen which is alpha to the carbonyl group. It may be a ketone, R may be an alkyl group, or R may be a H in the case of aldehyde. So, this alpha hydrogen is taken up by the base OH minus ion and we end up with a carbanion which is generated here, C minus which is generated, and this C minus is what is happening to this C minus? This C minus is getting in resonance with the carbonyl group to give you what is called as the enolate anion. So, enolate anion is the majority of the resonance is in the form of enolate ion, because the O oxygen stabilizes the negative charge more. But we have generated a carbanion intermediate in this case by virtue of the resonance of the intermediate. All the other carbon hydrogen bonds are not this much acidic because there is no stabilization of carbanion. So, in this case the stabilization is because of the fact that this negative charge is getting into resonance and the double bond is formed here and O minus is getting formed here, and we are getting an enolate ion. So, once this carbanion is generated in aldol condensation, what happens next? The next step is the reaction of this carbanion to another mole of the same aldehyde or ketone. Say if we had taken acetaldehyde with R equal to H, then we would have CH2 minus CHO, and this CH2 minus CHO is reacting with another acetaldehyde molecule. So, now what is happening here, that the carbanion which was generated in the previous step is acting as a nucleophile on this positively charged carbon of carbonyl group. This carbon is positively charged because of the polarization of pi cloud of the carbonyl group, we have already done in previous lectures, and the positive charge is attracted with this negative charge and a reaction takes place like this. The attack of nucleophile happens. So, carbanion is actually acting like a nucleophile here. So, we are talking about the generation of the carbanion and then the reaction as a nucleophile. So, what does it give? So, for your convenience, I have written it in this manner such that the product is more understood to you, because this carbanion part of the product would be appearing towards the right hand side. So, you can see that this reaction which is happening here is actually happening in this manner such that you get a product with CH2 of this carbanion here attacking the carbonyl C double bond O to give you a bond sigma bond, and the O minus would move to this O minus, this pi cloud would move towards the oxygen giving you the O minus. So, this form of aldol reaction happens where the carbanion is acting as a nucleophile. Then what happens in the aldol condensation? Then we this anion takes proton from the solvent and forms the aldol. So, this molecule is called as aldol because it has aldol, ALD means aldehyde or ketone wala ALD, and OL means an alcohol. So, a mixture of aldehyde kind of system and all. So, beta hydroxy aldehyde or ketone is formed in this case. But mostly the reaction does not stop here, and there is a dehydration reaction happening with this OH group moving out and one of the proton from this going out as a proton and this OH group moving out as OH minus to give you a loss of water molecule, and this alpha beta unsaturated carbonyl compound. So, this is the final product. However, the reaction is called as aldol reaction because of this molecule where an aldehyde kind of system and OL are present together, or we can say that beta hydroxy aldehyde or ketone is present here. So, this is all about aldol condensation. Then we move on to another type of reaction, which is the Claisen condensation. So, you would understand the concept we did in earlier lectures about the nucleophilic addition and nucleophilic acyl substitution. So, in the previous case what we did was, it is a case of nucleophilic addition. The nucleophile adds here and this C double bond O group gets converted into a C. This carbon is this one, this carbon. So, this gets converted into CO minus and a hydrogen adds. So, in totality from a C double bond O, we are ending up with this group added and the hydrogen added. So, two things are added, and the total reaction is an addition reaction. So, this is an example of nucleophilic addition reaction, the aldol condensation. It is an example of nucleophilic addition reaction. What is happening in Claisen condensation? It happens in a similar manner as with the case of aldehydes and ketones, but the difference is that the other R group which was present in aldehyde ketones carbonyl compounds, in the case is OET I have placed. So, this molecule is no more now a carbonyl compound, but it is a carboxylic acid derivative, or we can say that it is an ethyl ester, and we can also name it because I have given a complete structure of the molecule. So, we say that this is ethyl acetate CH3CO2ET. So, this is ethyl acetate which is a well known solvent also and an ester. So, what does it do when it reacts with O minus OET minus? Ethoxide is acting as a base again, and this in the similar manner to the aldol condensation abstracts a hydrogen, a proton H plus, and leaves the negative charge on the carbon atom, this CH2 group. So, CH2 is again a negatively charged system. Again this carbanion which is generated in the reaction is stabilized by virtue of the resonance, and we get the similar kind of structure, although the type of system is not an enolate kind of system, but we are having a OET group here also. So, this is the stabilization again in a similar manner to the aldol condensation. Now, the reaction again is attack of nucleophile, as in the case of previous aldol condensation, the carbanion is again acting as a nucleophile, and it attacks the C double bond O group to give you a similar kind of an intermediate, the O minus ion intermediate, but the change happens in the following step. Now, because of the fact that we were having the two groups as CH3 group, you could see the previous slide in the video that CH3 group was present and this was R, they could not get out because they were kind of very strong bases or very poor leaving groups, and they were not able to move out. But in this case, what happens, this O minus comes back into as to give you a C double bond O kind of system, and this OET moves out as OET minus to give you with the loss of ethoxide ion, this C double bond O group is coming back. So, this was this C double bond O group which is coming back in this case, and hence this nucleophilic reaction ends up here. It does not go to dehydration because there is no OH now. So, it ends up here and gives us a nucleophilic substitution reaction. So, previous case was nucleophilic addition reaction because the C double bond O group was lost and we were ending up with COH and this group. But in this case, this OET group has been replaced from this OET group is not now there, and but this CH2CO2ET group is in this place. So, OET group is replaced by this whole of the carbanion. So, this is nucleophilic substitution reaction and specifically nucleophilic acyl substitution, and in this manner we get an very important compound which is called as an active methylene compound type called as ethyl acetoacetate or acetoacetic ester. Why I am saying that this is a very important compound? Because this compound itself is well known for its acidity or the formation of a carbanion. How it is giving a carbanion? By the loss of this one of the hydrogen of this CH2 group. Why it would lose again? Because of the fact that again this may be this is in the resonance type of structure, giving you this type of resonating structure, and if the resonance is from the other side, then we get this type of structure. By virtue of these three resonating structures, these active methylene compounds are much more acidic, or the carbanion is much more stabilized than the case with aldehyde ketones, where only two structures with the enolate ion were possible. So, there are other active methylene compounds also, like we replace this OET with another R group, so with methyl, acetyl acetone, malonitrile, and these compounds are also having much more stabilized carbanions than the simple aldehyde or ketone group. So, this was one of the type of reaction which was present. The other type of reaction which is present is the aryl nucleophilic substitution reaction. This is a very typical case when more number of nitro groups are present here, then OH minus ion attacks on the more positive charge carbon of benzene having chlorine with it, and we get a Meisenheimer complex kind of system, but we are getting here a negatively charged ion, a carbanion. So, this carbanion is again stabilized by resonance, and I have not drawn resonance again and again because this negative charge will be taken into the nitro group or it would be moving into the benzene ring, and when it would be here again, then it would be more stabilized. So, because of this stabilization, this aryl nucleophilic substitution reaction happens in the case of the halogenated benzenes only when we have a very high minus R group like nitro groups present in a large number. So, we get the picric acid kind of system only when this mechanism happens only when the nitro groups number is present to a very greater extent. So, we would be saying that this reaction would not happen in a simple chlorobenzene because of the fact that there is no stabilization of carbanion, and in case of simple chlorobenzene, if ever a nucleophilic substitution reaction happens, it happens by virtue of other mechanism, which is the benzyne mechanism. So, I would leave the topic at this point of time. Thank you for your patience. Hello viewers, in this session we would be talking about the reaction intermediates which are left with respect to our previous lectures, the free radicals and a little bit of the carbanions part. So, starting from the carbanions, we would be talking about the generation and fate of the carbanion in the previous part, and we would be continuing with that. So, we have talked about the aldol condensation and the Claisen condensation reactions, and the other form of the formation of carbanion is the organometallic compounds. So, organometallic compounds are those in which there is a carbon metal bond. So, primarily we see the formation of organolithium compounds, which is in the slide you can see that organolithium compound is getting formed with the reaction of alkyl halides with butyl lithium, and we are getting a butyl chloride or butyl halide and RLi. So, this kind of system is organometallic, and because the metals are more electropositive kind of systems, so they will retain a positive charge and have a negative charge on the carbon system, which is the alkyl system here. So one of the example is organolithium. So how it is getting, what are the reactions they undergo, like by virtue of the reaction with carbon dioxide, the R group is acting as a minus, R minus, and it is adding on the C double bond O group of carbon dioxide to give you the R is attached to the carbon, and the O, which is negatively charged, attached to the lithium positively charged ion. So here also the alkyl group or the carbanion is acting as a negatively charged system, and which is acting in this reaction as a nucleophile. So this nucleophilic reaction again happens, the other molecule of RLi again add on to this C double bond O group to give you a dilithiate kind of system, which on hydrolysis gives you OH first, the lithiums are exchanged by the protons, and there is a loss of water because geminal diols do not exist. They straight away go into to form the ketones or the aldehydes, the carbonyl compound. So in a similar manner to this case, the other kind of compounds which are formed in the category of organometallic compound is the Grignard reagents. So the Grignard reagents, what are they made up of? They are made up of the alkyl magnesium halide. So one point I would like to mention here is that I have told you about organolithium compounds and Grignard reagents here, but organolithium compounds are much more kind of a pure or true carbanion kind of systems, because of the presence of lithium or very highly charged, positively charged system of the alkali metals. The system is purely ionic kind of system. So we can say that there is a minus charge and a plus charge, but in case of the Grignard reagent, the minus charge and positive charge are, which I have presented here, are notional, and just to understand that this is a negative kind of carbon which is utilized here, but this bond of alkyl magnesium bond is polar covalent, not completely ionic. So you should understand this point. So what are the reactions in Grignard reagent? Whenever you do in detail, you can study all the reactions. I have placed only two reactions here. One is the reaction with active hydrogen compounds like water or the alcohols or the amines. So what they do, the R minus part or the negatively charged part, polar negative part, abstracts a proton from these compounds to give you RH or the alkane, and the magnesium halide part goes as MgXOH. So it does not matter to us because we are much more interested in RH part, and this is one part why we have taken the dry ether here to prepare the Grignard reagent, because if water is present or this dry ether is also alcohol free, if water or alcohol are present in the preparation of Grignard reagent, immediately the Grignard reagent would be destroyed to give you the alkane. So the Grignard reagent is prepared in the solvent which is absolutely dry and alcohol free. Now for the second type of reaction, this R minus, again I have placed it notionally so that I can make the things easier for you to understand that this is a acting as a nucleophile again. So this reacts on the carbonyl compound to give you this kind of a system. This R is adding on to here, this R dash or this CH3 may be an alkyl group or an or a hydrogen. So if both the groups are hydrogens, it is formaldehyde, and if one is CH3 and the other is H, then any other aldehyde, acetaldehyde, and both the groups are R, then it is a ketone. So what happens in the last, this OMGX system is hydrolyzed with water to give you an alcohol. So if you were having a formaldehyde, you will end up with a primary alcohol. If you were having any other aldehyde, acetaldehyde or propanaldehyde, then you would be having a secondary alcohol because this R dash will be H there. And if you are having both the groups as alkyl groups, then you will be ending up in the tertiary alcohol as it is present here in the case of the ketone which I have taken here. So this reaction also happens in case of esters. So R minus or Grignard reagent attacks in case of esters also, and this gives the OR kind of system here, and again the next step is kind of a Claisen kind of condensation type of reaction which does not protonate the OMGX but gives a substitution reaction. This OR dash minus thing goes away to give you a ketone, or if there was the other H was no, in this case there would be a ketone only, because we are taking the ester. If you had taken the formyl ester, then maybe an aldehyde would appear. So the reaction does not stop here, and another group of R adds on to give you finally a tertiary alcohol in case of the esters. The fate and generation of carbanion is this much. Sometimes in case of the beta keto esters, or in some special cases the carbanion may be generated by the decarboxylation reaction, as it is happening in this case, like the sodium salt or a metal salt of carboxylate ion. You get this decarboxylation done and the R minus appears, but this R minus needs to be stabilized with something, as I told, as I have already said, that it is in the special cases of beta keto esters or beta keto carbonyl compounds. So this is all about the generation and fate of carbanion. Next we move on to the free radicals. So the next intermediate is the free radical. What is a free radical? We have talked about when we started with the reaction intermediates. The free radical is the intermediate in which the reaction happens in a homolytic manner. Thus the fourth bond, which was a carbon, it may be a carbon hydrogen bond, it may be another bond which is broken by equal sharing of electrons. So one electron of carbon is left with the carbon, and the other group or atom takes away its electron, such that an odd electron system is formed. This is neither a positively charged system nor a negatively charged system. It is an odd electron system, like hydrogen radical is present, which is nothing but which is obtained by H radical by breaking off this carbon hydrogen bond. So it is nothing but a hydrogen atom in a reactive state. So this is a free radical. What is the structure of free radical? It is kind of debatable because of the fact that the absolute structure is known to us. We say that it's a planar carbocation type of structure with a pure p orbital having an odd electron system. But in case of some inorganic things I have known, so these odd electron systems are placed in a hybridized orbital, as in case of carbanion. So need not to confuse with it. In organic free radicals we take it as a planar molecule, but this planar or sp2 hybridized free radical is somewhere in between an sp2 and a sp3 hybridized system. So if I place the CH all the atoms as H, so CH3 radical, then this system is known to be towards more of a planar kind of system. But as we increase the electronegativity of the atoms attached and we move on to a CF3 radical kind of a system, then we say that the structure is more like a carbanion kind of a trigonal pyramidal type of structure, and or we may say that it is typically a bent form of the sp3 hybridized form of carbon. So not going into details of those things, we move on to the stability of free radicals. Again we have done it in the hyperconjugative part. The methyl radical, I am taking an example of ethyl radical because methyl radical does not undergo hyperconjugation because of the absence of a carbon-carbon bond. So alpha hydrogen of this CH3 group, when written like this, the H is carbon hydrogen sigma bond is giving up the to form a carbon-carbon double bond. So hyperconjugation was a no bond resonance kind of system where this radical will move into an overlap of this carbon hydrogen sigma bond to give you a pi bond. This can only happen when the free radical, which we talked about in the previous structure slide, was sp2 hybridized. So this favors the sp2 character of a free radical, and hence this type of a hyperconjugative system is present. So we have 3 hydrogens in this methyl. So one hydrogen will give this type of a structure, the other hydrogen when will get broken up, then the hyperconjugative structure will be like this, and the third one would be like this. So, we have done this thing in carbocations also. So, we have 3 hyperconjugative structures in the ethyl case. So, what is the overall the stability factor? In case of ethyl, we have 3 hyperconjugative structures. Now, if we are having 2 methyl groups, then the hyperconjugative structure will be 6. So, 6 structures, more number of hyperconjugative structure, more no bond resonance, greater is the stability. Hence, this isopropyl radical is greater stable than or more stable than the ethyl radical because of more number of hyperconjugative structures. Again, tertiary butyl radical is having 9 structures by virtue of 3 methyls, and hence it would be the maximum stabilized radical in all of these, and methyl radical is not having any hyperconjugation. So, it is the least stabilized form. So, this is also this overall stability quote will also be is also further established by the fact that we see a decline in the bond dissociation energy of the carbon hydrogen bond in when we go from methane to ethane to isopropyl or to propane for a secondary CH bond, and tertiary butyl case for the carbon hydrogen bond with this. As the bond dissociation energy is decreasing, so the carbon hydrogen bond is, that means it is more available for breakage, it is easily broken. Why it is easily broken? Because of the fact that it results in a more stable intermediate. A bond is broken in an easy manner because of the fact that the resulting product or intermediate is much more stabilized. So, the energy to form that intermediate is decreased, and hence a lesser amount of energy is required. If a higher amount of energy is required, say methyl radical, then the bond is kind of much more stronger bond. So, these two things correlate and go well with one another and establish the stability of alkyl free radicals. So, moving on to the resonance part, the resonance we have already done a lot of it in the carbocations and the carbanions, but the main difference in this case is that if we are having an allyl radical, this radical, the half of the, I am showing half arrows here, you need to show half arrows because only one electron is moving here and one electron comes from the carbon-carbon double bond. So, half arrow is coming here, making a proper double bond here, and one electron is moving to the carbon, so giving you the free radical here. So, this is the only point which is needed to be understood, because in case of carbocation we were moving this to this, and in case of carbanion we were moving this whole of the lone pair, and this double bond was moving again in here. So, in this case the resonance is showing the odd electrons moving by virtue of the half arrows. So, this is the allyl radical which is more stabilized than the free radicals we have talked about, the radicals which were of hyperconjugative stabilization. One point I would like to mention here is that these alkyl radicals are not said to be stabilized by the plus I effect, because this is an odd electron system. It is the electron is one electron less. So, we cannot say that a plus I group or a minus I group would affect. So, we only mention the hyperconjugative effect to describe the stability of alkyl free radicals. Coming back to the resonance, allyl free radical is much more stable than the alkyl free radicals, and benzyl radical PHCH2 is much more stabilized than the allyl radical. Similar to the carbocations and carbanions, as we increase the phenyl ring, number of phenyl rings, the triphenyl methyl free radical is the maximum stable, and again as the salts were present. So, this is so stable that it can be stored at a certain temperature, it can be stored, triphenyl methyl radical. So, the stability increases because more number of phenyl rings are present there. So, because there is no stability by virtue of the aromatic character or other character, we straight away move to the generation of free radicals. So, generation of free radicals may happen by two ways. One of the factor is the thermal cleavage. The thermal cleavage, this is a peroxide compound. So, because I have taken R C double bond O. So if R is phenyl group, then I would say that it is a benzoyl peroxide which is present here. What is happening when I do the heating, or the benzoyl peroxide or any alkyl peroxide is heated with to a certain temperature, this oxygen-oxygen bond of peroxide is broken in a homolytic manner. Again, these arrows are half arrows, and half arrows depict that one electron each is shared, and you would see that R C double bond O O radical, and this would also give you R C double bond O O radical. So I have placed a 2 here, that means 2 moles are formed of benzoyl peroxide radical in this case. And this does not stop here because of the fact that this peroxide radical is again unstable, and this gives the electron to this carbon oxygen bond, and this alkyl RC bond again gives one electron to give you a double bond here, and this RC bond is broken up to give you a R radical, 2 R radicals, and the carbon dioxide is, which is formed by virtue of this carbon double bond O, is lost to the environment or the system. So we end up in generating 2 alkyl radicals from one benzoyl peroxide, or we can say 2 phenyl radicals from one benzoyl peroxide molecule by the loss of carbon dioxide. The other form, the other reactions which may generate a free radical are from diazo compounds. So in case of diazo compounds, again this part gets cleaved to give you Rn system R radical and N radical. Here also R radical and N radical. So we get 2 R radicals. These 2 nitrogens will be having 1 electron each from the breakage of 2 nitrogen carbon bonds, and those 2 odd electrons combine together to form a third bond between nitrogen and nitrogen, and that nitrogen triple bonded to nitrogen is nothing but the nitrogen gas, and it is evolved in the system, and we end up with the alkyl radicals or any phenyl radical also. So this is another form of generation of the free radicals from diazo compounds. So you can just miss part. This is a mistake. Minus CO2 R should not be here. We end up the reaction here. The third point is the reaction of tetraethyl lead. You would remember that tetraethyl lead is talked about as an anti-knocking agent in case of when we talk about the petroleum and the gasoline kind of thing. The anti-knocking agent is because of the fact that this lead is giving this on thermolysis or thermal cleavage, there are 4 ethyl radicals which are generated. So these radicals are also generated from tetraethyl lead. And one thing more I would like to mention here, that the free radicals are very much important for the fact that we are having free radicals presence in our body also, and thus there is a lot of talk about like we should eat more of the foods rich in antioxidants. So what are antioxidants? They are nothing but the molecules which provide you free radicals. Why are they important? Because of the fact that, like the tetraethyl lead was used as an anti-knocking agent, and it was somewhere helping, those free radicals were helping in that procedure. Those antioxidants, when consumed, give you more of the combination with the free radicals present in our body. So by virtue of that, the free radicals in the body are absorbed or demolished or diminished, and hence those free radicals do not interfere in the reactions with, say, the DNA molecules or the proteins, and they do not create the havoc or the chaos in the human body also. So free radical is of much importance to us because of this fact also. So coming back to the second type of generation of free radical is the photochemical cleavage. What is happening? In the presence of light, I have placed H nu here, and we get RCO radical and R radical here. This thing is not specifically for the alkyl radicals or aryl radicals, but also for chlorine Cl2 we just give light, it kind of dissociates into 2 Cl radicals. So this is all about the generation of free radicals. Now moving on to the reactions of free radicals. So the primary reaction which happens in case of free radicals is the chain reaction. So if you understand one type of reaction, you would understand all type of free radical mechanisms. So there is not much to talk about in every cases, but I have taken 2 cases here. One is the anti-Markovnikov's addition of the HBr to an alkene. So because we are talking about anti-Markovnikov, I have taken an unsymmetrical alkene with R group here, and there is nothing. So it may be a propene with R equal to CH3, and we are adding HBr by the Markovnikov addition. If we are adding HBr on without the presence of peroxide, what is the case in Markovnikov addition? That the Br goes to this second carbon and hydrogen goes to the more number of hydrogens wala carbon, because of the fact that that mechanism happens to be because of the carbocation, and Br minus adds later on. First of all, H plus adds, and there is a positive charge on the second carbon, making it as secondary carbocation. Here when we use peroxide, what happens, that the chain reaction is same again, we have done it, that R radical is generated, benzoyl peroxide is taken, heated to RCO radical, and then we get the R radical. What is the reaction which is happening again? In a chain reaction there are 3 steps. One is the initiation step. Here one R radical is generated, then this R radical reacts with one of the reactant which is HBr, and we get Br radical. So now the Br radical, which is the species which is reacting to the alkene, is created. So this part is called as the initiation part. The second part of a chain reaction is the propagation. So propagation means that this reaction goes on and on. You would understand in a bit that this bromine radical attacks this carbon-carbon double bond and gives you a isopropyl bromide radical. But if the reaction was happening on the second carbon, I am using again half arrows to show the depiction of a radical. It can attack here also, but it would lead to RCH Br CH2 radical. So that CH2 radical would be a primary radical, and that primary radical would be less stable than this radical. So this is the crux of anti-Markovnikov rule, that the secondary radical is formed when I am reacting through the first pathway, and so I would leave the second pathway and we will move on. The second step in propagation goes like this: isopropyl bromide radical again reacts with HBr, abstracts a proton from HBr and gives you the 1-bromo propane or 1-bromo any alkane, because I am using R here. So 1-bromo compound alkyl alkane and Br radical. Now what is a chain reaction? Chain reaction is one where the reactant bromide radical is reacting, and in a few steps it is getting created also. So this reaction has bromine radical going as a reactant, getting out as a product. This bromine again will attack on the alkene, again generate these 2 steps, again get generated. So this type of reaction where the reactant is keeping on generating again and again, goes on and on till the reactants, the alkene or HBr, are completely finished. So what will be the case when they would be finished? When termination happens. So termination can happen if in the following manner, like this isopropyl bromide radical combines with another isopropyl bromide radical. So there is no bromine generation in this case. So the reaction ends. Secondly, the CH radical reacts with bromo to give 1,2-dibromo alkane. The reaction gets completed. Thirdly, a bromine and bromine radical combine, and we get a bromine molecule. So these type of reactions are chain reactions, and they go by in 3 steps: the initiation, propagation and termination. So quickly we would go through another one type of reaction, which is another example of chain reaction, which is called as halogenation of alkanes. When we talk about alkanes, there is not much to discuss, but this reaction, which is halogenation of alkanes, what is happening? Chlorine is reacting with methane in presence of light again, and we are getting methyl chloride plus HCl. The problem in this, or the negative part of this reaction, is that the reaction does not stop here. If we are not having a good amount or good ratio of these two, then the reaction again goes to form dichloromethane, trichloro, that is the chloroform, and carbon tetrachloride. But we are focusing on the preparation of methyl chloride from this, and again initiation, chlorine gives 2 chlorine radicals, and we are having the propagation with chlorine reacting with methane to give you methyl radical again reacting with chlorine to give you methyl chloride as the product, and Cl radical. This Cl radical again goes into the chain and does the reaction till one of the two, the methane or the chlorine radical, are finished, and we end up with termination. So we have already talked about termination in the previous case, we need not discuss it again, and we complete this chain reaction here. Last but not the least, you can see the application of the allyl bromination using NBS. So you can just, this comes into the picture when we are doing the post graduation and all, and we see the N-bromosuccinamide. This allylic bromination of propene or any other allyl group is happening through a free radical mechanism. So that is all about the application of the free radicals, and we would be discussing the other carbene intermediate in the next lecture. Thank you so much for your patience.
Dear friends, due to paucity of time, we have to stop our lecture here. On that note, we would like to thank Dr. Khanna for coming to our show and delivering this wonderful lecture, and thank you dear friends for watching our show. Stay tuned and keep watching. Thank you.